questions you have up. Are there any questions that you've got you'd like me to go over from the work I assigned yesterday? Kinetic and potential energies. Actually, I have to specify. Kinetic or gravitational potential energies. Is there anything in there anyone would like me to do? Brooke, was that you? Okay, what do you got for me? Which B? 5B, 6B, or 7B?
6B and 7B.
Okay, here we go. 6 and 7. 6 says you're in a go-kart on top of a small hill. Yeah, you got to go. How are you getting home? Okay. Yeah, that's seems. I hope you have a good weekend. Yeah, you got to go. Okay, 6 and 7. 6, you're in a go-kart on top of a small hill. Your potential energy is 1,000 joules. The last time you checked, your mass combined with the go-kart was 100 kilograms, which is very light. What's the height of the hill? If you ride the go-kart down the hill, what will your speed be at the bottom? So, for part B, for 6B, you're cool with A, Brooke?
Yeah.
Okay. For 6B, it's the idea that at the top of the hill, you have this much potential energy and you're sitting there. As you ride down the hill, at this stage, we have to assume that no energy is lost because otherwise, I mean, it's a little bit more difficult. Colden over here is doing exactly that in my physics class right now. But you guys aren't there yet. So it's this idea that your initial energy has to equal your final energy. At the beginning, you start with a bunch of potential energy. At the end, you have a bunch of kinetic energy. And it's all of the potential, the 1,000 joules of potential energy gets turned into kinetic. So you're going to set this thing up as 1,000 equals 1/2 mv final squared, because it's your kinetic energy at the end. And then you know the mass. The mass is 100. So 1,000 is going to equal 1/2 times 100 times v final squared. So this is going to become 1,000 divided by 50 equals Vf squared. What's 1,000 divided by 50? 20? Yeah, I think it should be 20.
Yeah.
Equals Vf squared, square root. And so your final velocity is going to be whatever the square root of 20 is, which is going to be somewhere between 4 and 5. Does that make sense? Oh, and I've got the answers over here, so that's going to be 4.47. Presumably, B is going to be the same thing. Yeah, B is identical. In A, you find the potential energy. In B, you use that potential energy. It'll all be converted into kinetic, and you solve B the same way. Do you want me to do 7B, or are you cool with that? Okay. Yeah, B is exactly the same. 7B is the same as 6B. You just have to use 7A to calculate the potential energy instead. Anybody else have any questions, comments, concerns about any part of the homework? If you're away, the answers are here. Take a picture of this, or it's included in the video, both yesterday's video, which is up, and today's video, which will be up at some point in the next several days. I know I promised you guys yesterday that if I didn't have your biology tests marked by Tuesday, that you would get to go outside. I used that as extra, which you know I don't like doing. So I used that as extra incentive. Your biology tests are marked. They are in my ed. If you would like to see them, the grades you got on them, you may check my ed. You will get them back on Monday, when presumably we will have more people and more time. So all my blocks will get, both blocks C and D will get your biology tests back on Monday. Mr. Sapine, hello, sir. No, you're good, man. What can I, just stashing? Cool. You can just stash them up here if you want, on the desk right there. No worries. Whatever. I always, I want to welcome my guest anyway. It always interrupts. And they like you, so Okay, so today I want you to find me this page. If there are no questions about yesterday's homework, flip ahead, find me the page on elastic potential energy. Today's lesson is short. You stay on this page. I am going to flip back. When we spoke first about elastic potential energy, Jedediah, I believe it was you. You went for a walk. And we said, what about springs? Mechanical, kinetic, and gravitational potential we've been over already. We know what makes them scary. Kinetic energy, you should fear the mass and the velocity coming at you. In gravitational potential energy, you should fear the mass at a height in the gravitational field that we're in. And with springs, we established that it was the difficulty with which you have to yank on the spring. The harder it is to pull, the scarier it should be. And the further away you go, the more you should be concerned. Even if it is easy to pull, I mean, Jedediah, I think you only made it to the end of the corkboard. In the other block, you guys are D block, in my C block class, Vikram went all the way to like the couches. He just kept going. And I was more concerned with him than I was with you. And when he let them go, my ankles felt the difference between your extension and his extension. He extended it another probably at least 3 meters beyond what you did, and I felt it. It was different. And so then what is the expression that we're going to use for this? If we flip, I'm going to flip back to the page that you are on. Marcus, you're done? Fantastic. I'll take the whole thing, toss it in the bin. Your phone's right here. I don't remember which one's yours. This one? Okay, cool. Sorry? Yeah, in the B bin. B. You guys are B. No worries. Thank you. So that's the wrong page. We're flipping, finding this one. Today's lesson is on elastic potential energy and how we calculate it. So elastic potential energy is the energy that can be stored in elastic materials, and most materials, not all, most materials have a degree of elasticity to them. And you've seen a bunch of examples of this. Wood isn't stretchy, but it's bendy, and so there's elastic properties there. You saw that when we demonstrated the catapults that some of you guys built. Yeah, yesterday we demonstrated them. Your skin has an elastic ability to it. If your skin wasn't elastic, every time you grew a little bit, you would just tear through your skin, which would be a disgusting adventure. Your muscles have elastic properties. If your muscles weren't elastic, the tendons, ligaments, if they don't have a degree of elasticity to them, you would constantly be injuring yourself. So there's all sorts of materials that do this beyond elastics and springs. The elastic potential energy that shows up when you compress or stretch a spring from its original resting position. We call this position equilibrium. And springs are totally happy to remain where they are. Your skin is totally happy to remain where it is. But then you go and eat a big meal and now you're uncomfortable. Why are you uncomfortable? You're uncomfortable because you've stretched a whole bunch of elastic materials. Your stomach, perhaps the skin on the outside of you, and now you feel bloated. That feeling of bloat, of discomfort, is because you've stretched particular parts of your body beyond what they are at their rest state. We can do the same thing with springs. Jedediah did it with my ridiculously long spring, but I can do it with this spring too. This is a scale, which I'll demonstrate down here. But there's a spring in it, and we know we know how hard it is. I shouldn't use the language you haven't looked at yet. We know how hard it is to pull this spring. And so we can use that to actually determine what the weight of something is, or the mass rather, in grams, as we hang objects off of this scale. Take this. The farther you stretch or compress a spring or an elastic, lots of springs are meant to be stretched, some of them are meant to be compressed. The more you stretch or compress a string, the more energy it stores. So we've got the bow, the slingshot, just generic springs, and then one of my favorites, the Nerf gun. You pull the thing back, it locks into place. There's a spring inside there. You pull the trigger, lets the spring go. The implication here, though, is that you could upgrade your Nerf guns. And I have had students who in the past decided they were going to upgrade their Nerf guns because they weren't shooting hard enough. So they unscrewed their Nerf guns, opened it up, put a stronger spring inside, screwed the thing back together, and now they had a Nerf gun that would actually do damage when it hit you. They left it, and then they brought them to school to show me, and it was awesome. Bruise each other with Nerf guns, which you typically don't do. So springs have all sorts of cool little applications like this. The more compression or stretch there is, the more force or effort is needed to compress the spring further. Springs are one of these interesting things. You can stretch it to a particular length and hold it there, but if you want to stretch it further, you need to apply more force. So you've got a variable force or a growing force every time you want to stretch the spring further. Depending on the material the spring is made of, the design of the spring, the temperature you're at, all of these things, these properties can affect how much effort is required for springs and elastics to compress or stretch. This difficulty, we talked about it before, the harder it is to pull on the spring, the more you should fear it. We call this the spring constant. We give it the letter K. I don't know why it's K, but it's the letter K. And it is a measure of the amount of force needed to compress or stretch per meter. So every meter you want to stretch this thing, it'll require that much more force. Okay. So I want to go back to this thing. Here's my spring. The other piece that we talked about as it relates to, I want that one, that one is one. The other piece that we talked about as it relates to springs is this idea that the further you, or we're talking about how you stretch these things. And I want to be clear what we're talking about when we're talking about stretching springs. How long, just give me a ballpark, how long would you say that spring is? 2 centimeters. Maybe a little like 2 point something. We can all say it's 2. When we stretch the thing, so I'm going to hold it up here. We're going to stretch the thing. How long is it now? 5. Now, here it's 2. Down here it's 5. When we stretch these things, or when we look at the formula for the energy of a spring, and we talked about it kind of anecdotally before, we said it was the length that you stretched it that's going to have an impact on this. So if a thing started 2 and grew to 5, how far was it stretched? It was stretched 3. At its rest, the spring is 2. When I stretched it, it stretched to 5. And so it's this, and what I'm getting at is this picture here. It's the idea that we don't care about what the original length was. We don't care what the new total length is. All we care about is the fact that this thing was stretched a particular distance, and it's this distance right here that we're going to use to determine the energy in the spring. We're going to call that distance x. It's not the total length or the rest length, it's the difference between those two values. So the force or the energy now given to us or given to a spring is going to be given by this equation here. Where this equation comes from doesn't matter. You need some calculus before I can tell you that. But this is what we're going to call it. EPE, elastic potential energy. Also sometimes when I write it, or I'll give it to my grade 11s, my physics 11s, we'll call it PE, potential energy, SP. It's potential energy spring, is given by the formula 1/2 kx squared. It looks an awful lot like kinetic energy. Kinetic energy was 1/2 mv squared. For a spring, it's 1/2 kx squared, where k, that guy right there, is the spring constant, and x, the extension of the spring, gets squared right there. Questions, comments, concerns so far? Okay, then I'm just going to do one example for you, and then I've got a ton of questions for you to play with. Here's the example. We have a 20 kilogram box attached to a compressed spring, and we know that spring, we bought the spring from a manufacturer, and the manufacturer told us this spring has a spring constant of 300 newtons per meter. And so what that means is it requires 300 newtons of force to stretch the spring 1 meter. This thing that I was using only goes up to 500 newtons, 50 newtons, but you can only stretch this thing, actually we could figure this thing out. It was, just to give you perspective on this thing, if we stretch it 1 centimeter, boom. I'm at, is that 10? Yeah, let's say it's 10 newtons. So this little spring here, we'll just do an aside, this little spring here was 10 newtons, stretched it 1 centimeter, it gave me 1 centimeter's worth of stretch. So if I take this thing and I convert it into meters, 1 centimeter is 0.01 meters because there's 100 centimeters in a meter. And so if I wanted to figure out the K value, you can see here K value is newtons per meter. So I'm going to take my 10 and I'm going to divide it by 0.01. Oh, sweet, don't let them do that. 10 divided by 0.01 is 1,000. You may not connect to the TV. Who is this? An iPhone. Denied. Is that one of you guys? Or is it someone next door? I could assume it's not one of you. Put your phones away, gentlemen. You don't need to be doing this. Okay. Nope, I didn't ask. I just said that if they did it again, that we would allow it and we'd all look through their phone with them. Yeah, don't do that. If you want us to invade your privacy, don't try to jump onto my TV. That goes for you guys too. So anyway, if I have 10 newtons, 0.01 meters, that means that this thing is, this little spring here has a spring constant of, and you can see how hard it is to pull back. Like it's a little bit of effort. This spring right here has a spring constant of 1,000 newtons per meter. Just to give you perspective. So this particular spring that we have here is only 300 newtons per meter. It's easier to pull. What is the potential energy of the spring? We're told that this spring with a constant of 300 newtons per meter, the box is resting on a frictionless surface. We need this. We want it to be frictionless. And the spring is compressed 30 centimeters, which we are told is 0.3 meters. They've done the conversion for us. What's the spring potential? So EPE, and again, now that we know what we're being asked for, we write out the equation, 1/2 kx squared. We know K is 300 newtons per meter. We know X is 0.3 meters. We have to use the length in meters, and now or the extension in meters, and now we go back and we plug it into our equation and we find out how much spring potential energy has been given to this system. This will be 1/2 times 300 times 0.3 squared. And if you ram that through your calculator, what do you get? Sorry? Yes, I can give you a second. Boom. Okay. What's the number? Sorry? 13.5 joules, you betcha. Now, okay, part B says, when you let go of the box, and you intuitively you know what's going to happen here. Daniel, what's going on? Whoever's talking to Daniel in the hallway, go back to class. Intuitively, you know what's going to happen. We've compressed the spring, the box is there, we let go of the thing, it's going to fly forward. It's important that the surface be frictionless. Why do we want the frictionless surface? Why do we want the surface to be frictionless? What's friction going to do if we allow friction to act? Sorry? It's going to, what about energy? What's it going to do to the energy? Is friction going to add it or is it going to take it away? Friction, is friction going to speed up the box or is it going to slow down the box? It's just going to slow down, right? Friction is going to act against you. And so if friction is allowed to act, it will slow down the box. And if it slows down the box, then this is no longer true. The energy initial is not going to equal the final energy. Energy will not be conserved if we allow friction to act, which is what my physics 11s are doing right now. So we need it to be frictionless. Next year, if you take physics with me, we can figure out how we deal with that. But for now, we're frictionless. If it's frictionless, we know that the energy initial is going to equal the energy final. So the initial energy is all spring potential, EPE, and the final energy is going to be all kinetic. So then, how much kinetic energy is this thing going to have when we allow the spring to decompress? How much spring potential was there? It's going to be the same. It was 13.5 to start. If friction is not allowed to act, then all of the 13.5 is going to become kinetic energy. And so once we allow all of that spring potential energy to become kinetic energy, we can figure out how fast the box is going to move, which is what it's asking for here. How fast is the box moving after the spring releases the box? So this is now what we're going to look at. We know that the kinetic energy is given by the equation 1/2 mv squared. We know the mass, it's 20 kilograms. We know the energy, it's 13.5 joules. And so now I can go ahead and just like we did over the last couple of days, I can plug these pieces of information into that equation. I can figure out how fast this thing's going to go. So 13.5 is going to equal 1/2 times 10 times v squared. You done, Jack? Nice. In the bin, please. Here's your phone, sir. So, nope, this is 20. My bad. 1/2 of 20 is 10. Divide by 10, divide by 10, and we're going to get 13.5 divided by 10 is 1.35 is going to equal v squared. I don't want v squared, I just want v. So to undo the squaring, I got a square root. So how fast is the block moving once the spring is allowed to decompress? .16 meters per second. Which doesn't sound like a lot, but it's not nothing. It means that every second, the box gets to travel this far. It's pretty good for a 20 kilogram box. All you have to do is compress the spring. Any questions about what I've just done? Are we cool with the steps? Okay. And that's it. This is today's lesson. We've done a lot of the math already, so I don't feel like I need to necessarily review a lot of the math. We've made these connections before. That was yesterday's lesson, the idea that your gravitational potential and your kinetic energies are related to each other. Energy initial equals energy final, because we're assuming that all of the energy is getting converted. Next year, you look at what happens when that isn't true. So then today, what I want you to take a look at is pages. This page is page number 3, because I took a bunch of individually paged documents and slapped them together. I want you to work on pages 3 to 7, all of it, for homework. I have an answer key for you. As you finish this thing, if you'd like to check it, you may. There's a graph. You will be doing some graphing. It's going to be great. If you've got questions for me, let me know. Otherwise, on your mark, get set, giver. Good luck.